The Balkan Mathematical Olympiad, or Balkan MO, as the name suggests, is a math contest held in one of the countries in the Balkan region of Europe. This competition was first held in 1984 in Athens, Greece, with the participants being just a mere 3 countries: Greece, Bulgaria, and Romania, which were the founding countries of the Olympiad. Now, I know you didn't click on this video for a history lesson, but I think this prologue is important to set the scene for the kind of problem we're going to be dealing with. The Balkan MO was originally designed to be a slightly more approachable, but by no means easy Olympiad, organised during the globalisation of the International Mathematical Olympiad, or IMO, which by this point had built up its prestige. Nowadays, there are 11 recognised member countries of the Balkan MO, which rotate to host the contest. A number of guest countries, including the United Kingdom, are also invited to participate in the competition. Similar to the more well-known IMO, countries send teams of 6 pre-university students to answer this 4.5-hour exam, containing 4 problems, each scored out of 10. Arguably more sensible than the 7 marks many other contests mark their problems out of. These problems are generally of increasing difficulty, so in simple terms, the last question is really hard, especially given the time constraints. Now, that's enough random information, which at best might help you win your local maths history trivia, if that even exists. Let's delve into the actual problem at hand. We will be taking a look at the last question from last year's, that is the 2023, Balkan MO. This problem involves everyone's favourite 2 protagonists, Alice and Bob. We are asked to find the greatest integer k, less than or equal to 2023, such that whenever Alice colours exactly k of the numbers in the set 1, 2, all the way up to 2023 in red, Bob can colour some of the uncoloured numbers in blue in such a way that the sum of the red numbers is the same as the sum of the blue numbers. This problem statement is actually quite easy to grasp after a first read, but solving it is a whole different animal. The students during the exam probably felt the same, given that the entire fleet of silver medalists scored full marks on the first 3 problems, and then 1 out of 10 on this problem. Yes, all 22 of them got this exact score. The gold medalists were those who made further progress on this problem, and only 1 person in the entire competition scored full marks on this question, getting a perfect score in the process too. Scrolling down through the graveyard left by this question, we do also find this score of 8 out of 10 on this problem, but there aren't any other notable outliers. This problem really was a killer. Now, let's try and solve it. We need a general plan of attack. Luckily, almost all maximization or even minimization Olympiad problems follow the same pattern. First, find an upper bound for which the result holds. Show the result holds at this upper bound, but just as important, prove the result fails for values greater than this upper bound. It turns out that the second half of this proof, which is proving that the result fails for values greater than some upper bound, is a quote-unquote easy part of the problem, responsible for all the people gaining 1 mark out of 10. But before tackling this main problem, I want to solve a simpler but similar problem in nature. The question is, given the set of numbers from 1, 2, up to 100, find the smallest integer k such that any subset of size k contains at least 2 elements with an odd sum. This, like our main problem, is about finding a bound, although in this case we're minimizing. I'd encourage you to pause and try this one yourself. You might observe that if all the elements of our set were even, then no 2 can have an odd sum. There are 50 even elements in our set, so we know that k is greater than 50, which we may conjecture as being our lower bound. Now, we must show that if k is greater than 50, then 2 elements must have an odd sum. Sometimes with these problems, proving a stronger result, which implies our desired result, turns out to be easier. In this case, we may observe that pairs of consecutive numbers have an odd sum. Hence, showing that the subset contains a pair of consecutive numbers would suffice. We can pair up the numbers into 50 disjoint pairs, as shown, but a subset with greater than 50 elements must contain 2 elements from the same pair, which, as we established, have an odd sum, as required to give k equals 51 as our lower bound. There are 2 key takeaways from this mini problem. Firstly, this idea of proving a stronger result, which implies our desired result, may be easier. But secondly, this technique of pairing up numbers and producing inequalities will be crucial to the main problem. Returning to the main problem, I told you that the first mark was fairly easy to get. Observe that if Alice can choose enough numbers such that her red sum is greater than all the remaining numbers, this makes Bob's task impossible. A bit of brute force computation shows that the sum of the 593 largest numbers in our set is the following number, which is greater than half the sum of all the numbers in our set. So even if Bob coloured all the remaining numbers in blue, he wouldn't be able to reach Alice's sum. From this, we get that k is less than 593. A remark I want to make before we proceed is that a key differentiator between contest maths and research maths is that there's often an elegant reason as to why a problem is written. It turns out that this problem is no different. The above constraint is in fact the only constraint on k, which means the crux of the problem is to show when k equals 592, Bob's task is always possible. Spotting this in an exam, especially after solving 3 extremely hard problems, is no easy feat, but it does make the job a lot more achievable. One approach to finding a strategy for Bob when Alice colours 592 of the numbers in red could perhaps be found using a greedy algorithm. As the name suggests, the overarching concept of a greedy algorithm is to be greedy and repeatedly choose the largest of the remaining numbers to colour in blue without exceeding the sum of the red numbers. Adding some notation, what we're doing is considering the following sum, beta j, where the sequence b1, b2 and so on are strictly decreasing uncoloured numbers, so b1 is the largest. For convenience, denote the sets of red and blue numbers as a and b respectively, with the sum of Alice's set being alpha. So the sequence we defined are strictly decreasing elements in the complement of A. The way that we set up this greedy algorithm is to greedily choose the largest I such that the sum beta I is less than alpha. Then, we might try to fill in the gap between these two sums, but this is tricky and just intuitively speaking doesn't seem always possible. It should be apparent that blindly applying the strategy is unlikely to work in all cases, since it's possible that at some point we will run out of numbers to colour which make sure that the blue sum does not exceed the red sum. However, this thought has helped us gain a better grasp of the problem we're dealing with. We shall now move on to the main solution to prove that k equals 592 is maximal. Like we did, define the sum of the 592 red numbers as alpha. Now, we will employ the strategy of proving a more specific result which implies our desired result. Consider letting alpha equal 2024a plus b for some b between 0 and 2023 inclusive. This step seems extremely arbitrary, but it leads to an incredibly clever construction, so bear with me. First, consider the case where a is non-zero. Bob aims to colour one pair of numbers whose sum is b, and a pairs of numbers whose sum is 2024. So the sum of these a plus 1 pairs is precisely alpha. To proceed, consider the following pairs taken from our original set whose sum is b. To avoid overcounting pairs, we've taken the first number in each pair to be the smaller of the two. For example, when b equals 7, these are the pairs. We have floor of b minus 1 over 2 such pairs, but this isn't enough to guarantee that Alice hasn't chosen at least one number in each pair. This is where the second clever insight comes in. We say that Bob can instead colour one pair of numbers whose sum is b plus 2024 and a minus 1 pairs of numbers whose sum is 2024, which again all sum up to alpha, noting that a must be non-zero for a minus 1 to be non-negative. Now, why is this helpful? Well, consider the following pairs whose sum is b plus 2024. Note, we've strategically chosen only these pairs such that they are disjoint from the first floor of b minus 1 over 2 pairs we chose before. Therefore, we have floor of 2023 plus b over 2 minus b more pairs. Hence, the total number of pairs is the following sum. But removing these floor operations, this is greater than or equal to the following. And just like magic, the b term cancels, leaving us with just 1010. Therefore, we have more than 592 pairs of numbers, so Alice can't have possibly coloured at least one number from each pair, which means that Bob can find a pair with the sum of b, or b plus 2024, and hence, in total now, 594 numbers will be coloured. We've now passed the real hard part of the problem. The rest of the work is just cleaning up the details. We need to find our a, or a minus 1 pairs whose sum is 2024. We can list all 1011 pairs in the original set with the sum of 2024, and now it becomes clear why we wrote alpha in the form 2024a plus b in the first place. 594 numbers are coloured so far, so at least 1011 minus 594, which is 417 pairs, have both numbers uncoloured. Unfortunately, if we consider the maximum value of a, since alpha is at most half the sum of all the numbers, the following inequality simplifies to a is less than or equal to 505, which isn't as strong as the bound of 417. This is where the third beautiful idea comes in. If we have two sets, a and b, with the sum of alpha, then the remaining numbers have a sum of s minus 2 alpha, where s is the sum of all the integers from 1 to 2023. That is equivalent to saying we can find a subset of non-red numbers, that is, in the complement of a, with the sum of alpha, if and only if we can find a subset of numbers in the complement of a with the sum of s minus 2 alpha. Just take a moment to let that all sink in. With this newly found knowledge, we can define some quantity, alpha dash, to be the minimum of alpha and s minus 2 alpha. Critically, this quantity, alpha dash, is less than or equal to a third of s, since we divided the set into 3 parts, so the minimal part is at most a third of the total sum. This means if we go back through our argument and replace every time we refer to alpha with alpha dash, we can obtain the same conclusions, but now there's a stronger bound on alpha dash, and hence on a. Rearranging the following inequality gives that a is less than or equal to 337, which is less than 417, our bound from before. So, as required, Bob can find a, or a minus 1 of these pairs with the sum of 2024, so Bob can colour numbers blue with the sum of alpha. This completes the problem in the case where a is non-zero. Now, we just have to tackle the case where a equals 0. so alpha dash is less than or equal to 2023. Since k equals 592, the minimum value of alpha is the sum of the smallest 592 numbers, which is greater than 2023, so we know that alpha dash must be s minus 2 alpha. We can immediately notice that if alpha dash is greater than 2 times by 593, then we can consider the following 593 pairs with a sum of alpha dash. Alice can't have coloured at least one number from every pairs, since she only coloured 592 numbers, so one pair can be coloured by Bob in blue to get a sum of alpha dash. Then, when alpha dash is less than or equal to 2 times by 593, a more qualitative observation we can make about this case is that Alice's sum, alpha, is really large, since this quantity alpha dash is very small. In particular, we can rearrange that alpha dash is less than or equal to 2 times by 593 to get that alpha is greater than or equal to the following. But the last clever insight is that this quantity is at least the sum of these 592 numbers in our starting set. This means that Alice can't have chosen any number less than 839 to colour in red, so Bob can readily choose one or two of these numbers less than 839, which sum to alpha dash. And finally, after all that, all the cases have been checked, and this problem is now solved. Maybe you thought that was the end of the video. We've solved the problem. But recall that I mentioned greedy algorithms. We fairly quickly ruled out the existence of a solution using a greedy algorithm, and the problem writers did the same. But if you remember, the second highest score obtained on this problem was 8 out of 10, and this wasn't by any of the gold or silver medalists. In fact, the solution which obtained this score used the concept of a greedy algorithm, with a few minor omissions, but it was set up in a way which is far from obvious. Define the sum beta j in the same way we did before, and let I be the minimal index such that the difference between alpha and beta I is less than bi, in other words, less than the smallest term of our sum. This is subtly different from the first way we tried to set up our greedy algorithm. Note, since the sequence b1, b2 and so on are strictly decreasing, such an I must exist without beta I exceeding alpha, so their difference is non-negative. Call this non-negative difference delta. Then, if delta equals 0, or delta itself is in the complement of A, in other words, delta is uncoloured, then Bob is done by colouring all the numbers from b1, b2 up to bi, and then colouring delta all in blue. We can suppose for a contradiction that delta is in A, or in other words coloured red, and no such set B with a sum of alpha exists. Our aim will be to show that if this is the case, then beta I is greater than half the total sum, which would contradict beta I not exceeding alpha, since with k equal to 592, alpha cannot exceed half the total sum, s. The assumption implies that every pair with the sum of delta in our original set must have at least one element in A, otherwise Bob would readily colour one of these pairs and the terms in the sum beta I in blue and be done, noting that delta is less than all of these terms, so we don't count the same number twice. Slightly less obviously, every pair with the sum of delta plus bi must also have one element in A, because then Bob could colour the first I-1 terms in the sum beta I, and one of these pairs to reach a sum of alpha. Again, we've strategically chosen only pairs which are disjoint from the pairs with the sum of delta. I think it's worth it to look at a specific value for bi and delta to see what these floor function terms are actually doing. But essentially, they ensure our pairs are disjoint, we don't count the same pair twice, whilst maximising the number of pairs we consider. In total, we have considered the following number of pairs, but this is greater than or equal to the following expression, which simplifies down to bi over 2 minus 2, but we need this to be positive. This gives us two edge cases where this would be negative. If bi equals 1, then delta equals 0, which would break our assumption. But when bi equals 2, then delta equals 1, or 0, but we just handled that case. So 1 must be coloured in red. But this implies that beta I contains every number in the complement of A, which would be greater than half the total sum, S, which is greater than alpha, and is hence a contradiction. Outside these edge cases, we note that all the numbers in every pair have been strictly less than bi, but since delta is in A and was not in any pair, we get that of the set 1, 2, all the way up to bi minus 1, at least the ceiling of bi over 2 minus 1 elements must be in A, in other words, coloured red. Since k equals 592, at most 592 minus this quantity of elements in the set bi plus 1 up to 2023 are coloured in red, which can be simplified to 593 minus the ceiling of bi over 2. Hence, using the definition of beta I, all the numbers in the set bi up to 2023, if not coloured red, are coloured blue by Bob, so I is at least 2024 minus bi minus 593 minus the ceiling of bi over 2, which simplifies down to 1431 minus the floor of bi over 2. Also, since k equals 592, the number of red elements in the set 1, 2 up to bi minus 1 is at most 592, so bi over 2 minus 2 is less than or equal to 592, so bi is less than or equal to 1188. We handled the case bi equals 1 or 2, so the final goal is to show that for bi between 3 and 1188 inclusive, that beta I is greater than half the total sum, S, the contradiction we're looking for. Considering the minimum values of the sequence b1, b2 up to bi, we get that beta I is at least the following sum. But substituting in our inequality for I in terms of bi gives the following. But using the sum of the first natural numbers formula, this simplifies down to a quadratic in bi, which if we do some messy algebra to by completing the square or differentiating obtains its maximum at 2863 over 3. Finally, if we check the extreme values of bi, which are 3 and 1188 in this quadratic, these are both greater than 2023 times by 2024 over 4, which is half the total sum of our starting set, S, which gives us our desired contradiction and completes our solution using a greedy algorithm. In conclusion, I think it's understandable why the Problem Selection Committee thought this problem would have been extremely challenging. The number of clever insights and edge cases which had to be considered individually meant that it was quite fiddly. Considering you survived to the end of the video, you might be interested in a couple of follow-up questions and generalizations of the problem that we dealt with. A natural question to ask is, what if we replace the number 2023 by some positive integer constant n? Perhaps there will be some further bounding on the maximum value for k. Also, what if k was the actual value of Alice's sum, rather than the number of elements that she coloured in red? Both of these related problems are super interesting extensions to our main problem. If you're fascinated by these problems, and the brightest young minds who are able to solve these questions under time conditions, look no further than the sponsor of today's video, Brilliant. Brilliant provides you with thousands of interactive lessons in maths, data analysis, programming, and AI, designed to improve your problem-solving skills to the level of some of the most talented Olympiad competitors and researchers. Their approach to teaching all starts from the first principles to help you understand the concepts from the ground up, with lessons crafted by professionals. Their hands-on approach is proven to be 6 times more effective than lecture videos, but personally, I was extremely impressed by the breadth of content available on Brilliant. I was once researching the properties of the reflection of the median of a triangle over the angle bisector, known as the summedian, and it turned out that Brilliant had just the course I needed. The interactive approach to geometry in the measurement course has been an absolute favourite of mine. If you can incorporate Brilliant as part of your daily routine, even just for a few minutes, this habit can be an absolute game changer. To try everything Brilliant has to offer, free for a full 30 days, visit brilliant.org/PolyaMath or click the link in the description. You will also get 20% off an annual premium subscription.